Okay, good afternoon, everyone. I guess you guys all hate me, sitting everyone at the back. Maybe come to the front. Come on. Anyway, you don't need to. I don't want to force you. Since I missed my office hours last week, and also many of you have project ideas want to talk to me, so I'm going to be around after class today. Also tomorrow, much of the day, but probably the best window is 3 p.m. or later. And at that time, if you come to me, I'll also discuss specific project ideas that I have. I haven't had a chance to pen them down. But several of you have written to me, so just sort of come by and speak with me. So today, let's see. Yeah, today come to my lab also, and tomorrow also in the lab. So let's plan on that. Okay, so I wanted to pick up where I left last Monday, which was we were talking about battery. We had a bit of a detour through short lecture by Bharat on kind of this life cycle kind of analysis, but sort of we'll go back to kind of on the more engineering technology end of things. So what I had presented on Monday was some of these characteristics of batteries, the non-idealities, which as I'd shown, they kind of impact the way you might operate the system. We basically saw a couple of non-idealities. One was the dependence on the current, namely the capacity that you actually get out of the battery depends upon the current or the power you are drawing from that. And the second was what? Anyone remember? What was the second non-ideality? So relaxation, the battery, you stop using the battery, it recovers. And that basically meant that under certain circumstances, it might be better for the protocol or the scheduler to not use a resource continuously, but rather run it for a while, stop, run it for a while. So you kind of deliberately arrange for the battery to kind of recover. So just generally speaking, this whole idea that somehow we need to take this non-ideality into account leads to a whole bunch of other things. So there's another angle to this battery, which is could you adapt the operation of the system depending on the battery level that is remaining. Okay, so what I mean by that is that if, for example, there is a task that is deferrable, as in can be shifted in time, then perhaps you might consider doing that. So that goes not so much into reducing the energy consumption, but rather kind of spending the energy at the right time, or perhaps at the right place. You might move it to a different node. So the ability for a platform, for the software to know what is happening to the battery is important. So there are several measures of it. One is kind of the state of charge of the battery, which basically says how much juice is remaining in the battery. And as we saw, it's a little bit of a function of your workload. But you can still say something about it. What's the peak remaining? And the other part is the state of health of the battery. And that matters also because if you have, for example, a big battery pack in which there are lots of cells, which is pretty much what happens. What we think of a battery is actually a whole bunch of cells inside them connected in some sort of a series parallel architecture. So as the health of a cell degrades, you might want to sort of take that into account, particularly in like EVs and stuff like that. That interconnect of cells itself is configurable to some extent, so you can kind of discard a cell, sort of bring it in, bring it out, those kind of things. How many times you have cycled a cell may matter, charge, recharge. So this visibility of the state of the battery to the software is important, and there are a bunch of different metrics behind it. So two main ones are state of the charge, and this roughly corresponds to kind of when your phone shows you X% battery remaining, that's coming from some sort of a fuel gauge, if you may, out there. And the simplest so firstly, one thing, you cannot really have a sensor in the battery which basically says this is the battery level. There is no such direct measure you have. So there are only indirect measures that can give you access to how much battery is remaining. So methods include that if you have access to the innards of the battery, which can work with like lead acid batteries and all, then you can have some sort of stuff in there which looks at the concentration of the electrolyte and then translate that into some sort of a number for you. But kind of batteries we find in our mobile devices and all are not like that. So that's out of question. The second one is using voltage as a proxy. And kind of the idea is that as the battery discharges, the voltage drops. We saw some curves like that last time. And perhaps I can translate that into a level of battery which is remaining. And so unfortunately, the problem out here is that this voltage is fluctuates quite a bit in the sense. So firstly, when we have that relaxation phenomenon that I talked about, then we stop using the battery, the voltage goes up. Okay, so that would kind of suggest that there is more capacity remaining in the battery than generally is. So that's one part. The other thing is that voltage is also impacted by a whole bunch of other parameters, which is why in these devices, the percentage battery remaining is kind of it tends to be a bit flaky, to the extent that in the latest generation devices, Apple actually doesn't no longer promise in terms of how much time or stuff like that remaining, because these are kind of measures that are hard to get. Part of the problem is that every battery is different and its usage is different. So the way one user may be using it versus a different user is using it would differ. And I recall in some of the products that Apple, again, since I tend to use Apple products, so those are my examples. So they will make you go through this rigmarole of calibrating the thing, like charge the battery fully, then discharge it fully so that it gets a range of what is happening. These were earlier batteries which had effects like memory effects and all, which would sort of kick in. So this kind of stuff can be done, but requires careful consideration for all these other sort of factors which you have to compensate for. Otherwise, you will see all these weird phenomena, percentage battery going up, stuff like that. So you want a reliable fuel gauge to be one which kind of gives some reasonably accurate and monotonic representation of what's happening to the battery. So voltage as a proxy, and this is easy to do otherwise because you basically just need some sort of voltage sensing thing across the battery. Then the next one out here is essentially you count how much load you are drawing. So you keep track of voltage and you keep track of the current that you are withdrawing, and then you do an integration of that. So essentially at the output of your battery, there are conceptually two resistors, also two voltage sensing. One is you're measuring the voltage of the battery, and the other is you have a very low resistance in series with the battery, and you measure the voltage drop across that, and that gives you the current which is going through, or you have some other way of measuring the current, and then you integrate over time. Again, all these methods have sort of various kind of calibration kind of issues, so does this. Then there are sort of more sophisticated methods which basically model the battery in terms of some sort of a parametric model which you then track and what is happening. A lot of control theorists work in this space and all also to kind of try to come up with good models. Battery is a highly nonlinear kind of phenomenon, but you could imagine that I mimic the battery. So I computationally maintain some sort of a model of the battery, and then as I'm withdrawing from the battery, I kind of update that model. And in that model, I can see how much time is remaining. So I kind of mimic that. There are also certain battery chemistries may have other physical parameters internally which can kind of indicate this. There have been efforts towards where they would instrument the insides of the battery with sensors and then get to know things. Not viable for laptop, mobile phones and all, but again, if you're working with a big EV or a grid battery pack and all, then they become desirable. So that's this is basically these methods are basically saying how much battery is remaining. There is another sort of there are other measures which correspond to this. So like how much discharge has happened as opposed to how much is remaining as to sort of how much I have discharged. A second measure of battery is the health of the battery, state of health, and that's important as well because this begins, so it's not so much of an issue in our mobile devices and all, because if our battery health has degraded, then you're probably going to get the battery replaced. But in bigger systems, if the health of certain cells in my battery pack has degraded, then I will use those cells differently because we don't use all the cells all the time. So state of health is, it's not like a physical quantity that you can say, oh, how much charge is remaining. It's kind of a made up number, but it's basically saying I want to assign some sort of a metric to the battery saying what is its state of health. So think of it like a number between, let's say, 0 and 100. 100 means perfect health, 50 means, okay, kind of not that healthy, and 0 means it's dead or something like that. Okay, so some sort of a state of health metric that we want. Its units typically are sort of percentage health remaining, and some sort of a threshold is used to indicate that. Now the challenge out here is it's a multidimensional metric because there are many aspects of battery health. One of them might simply be how much charge can it hold, how much it has aged, how many cycles of charge discharge have I done, all those kind of questions. So there is no particular physical quantity, and moreover there is no particular consensus as to what this metric is. So lots of papers and different people kind of use different things, but it would be some combination of all these things that are listed there. As batteries begin to age, perhaps its internal resistance and all go up. Its capacity is degrading, the voltage has degraded, the voltage charges to exhibiting a high degree of self-discharge, ability to be charged. I'm not going to charge it up to the same capacity I could. How many charge-discharge cycles I have done. All of these somehow go into a composite made-up number, which we call a state of health. And as long as kind of it meets the goals of your system, you are okay. And as I mentioned, this becomes an issue when you have battery packs with lots of cells in them. We put cells in series if the voltage of an individual cell is not sufficient for our needs. So like for example, the voltage of a cell is decided purely by the chemistry. So you can't control it, okay? It's whatever the chemistry is. Lithium ion would have something, NiCad would have something. And then your circuit or load is designed with certain voltage in mind. Typically you take the battery output, you feed it into what is called as a voltage regulator, which kind of actually generates the actual voltage rest of your circuit uses. So batteries may need to be put in series, and then you put them in parallel to achieve redundancy, to achieve higher current value and all. So one of those cells goes bad, you have an issue. But worse, what happens is that when you have these kind of cells, unfortunately, some of the cells may not be identical. So let's imagine, because of manufacturing variations and all, I put two cells, and those two cells are sort of not quite matched. So what may happen is that imbalance in their characteristics will cause an imbalance in their use. So if I had two identical cells in parallel, and I drew a certain amount of power, both of them will be penalized equally. But if one of them, let's say for example, is different than the other, then what will happen is I'll end up using one of them more than the other, and therefore their state of health will degrade more rapidly for one cell than for the other. So, and likewise, if we have things in series, I may end up using one cell more than the other because of these asymmetries or these variations that exist. So mismatch can lead to overcharge. I have two cells, I'm trying, again in parallel, I'm trying to charge them. One cell reaches its capacity sooner than the other, and therefore I am left with two choices. Either I charge one of them fully and leave the other one partially uncharged, or I overcharge one of them. Both of them carry negative consequences. As the cells age, they lose capacity, and their parameters diverge even further. So they may start out being identical, but minor changes in the way we use. It could even be that one cell was at the inside of the battery pack and the other cell was towards the outside of the battery pack, and they're seeing different temperatures. So over time, they age differently. and then again those parameters will diverge, and we'll end up with the situation where sort of kind of a positive feedback loop where the one cell begins to more rapidly degrade over time. So uneven aging, and that leads to kind of the weaker cells getting even weaker and aging even faster. So a lot of so partly state of health goes into this view. That is, once I begin to see this kind of imbalance, then software kicks in. Essentially, these are battery management software. So this is stuff typically either inside the battery pack or really low-level software sitting somewhere in the system. It's managing all this part about the battery. It's monitoring its usage, it's monitoring its state of health, and it's continually kind of managing the process so that my overall battery pack remains healthy. So particularly kind of in bigger systems, this plays a very important role. So what? Let's see if I can. Yeah. Okay. So there are a variety of reasons why mismatch can happen, but very crudely, one of the reasons, for example, the mismatch happens is that the state of charge is different. That is, amount of charge which exists in the battery is different. And the other one which happens is that if the capacities that those cells have different, and again, that's an effect of the parameters gets magnified over time. So the way to kind of cope with these kind of things is that, again, as part of the battery pack, there are efforts made to make the things balance out. So you want to make sure that when I'm charging, everything is charging equally. When I'm discharging, the load is equally distributed. If I have cells which have some variation, perhaps I can do some sort of a compensation for those variations. So for example, I'll deliberately put less load on the weaker cell and I'll put more on the stronger cell. If I know that one cell will charge sooner, its capacity is lower, then I will charge it at a slower rate, or I'll stop charging it at some point, so that again I balance these things out. So several different approaches are done. There are kind of, you can design certain passive circuits so that sort of your battery pack behaves in a nicer manner, but more typically or sort of better is if you have some sort of active approaches, essentially a control system running and actively managing the charge discharge process. So you don't simply let, when you're drawing the current, it's not simply whatever I get, but rather the circuit intervenes with some sort of a control software and is actively kind of controlling how much am I discharging from different cells or how much am I injecting into the different cells. And so your batteries actually, by the time you hit laptop kind of things, the battery packs have a processor inside them. There is a serial bus going to the battery, and inside the battery all this control happens. There was a 2-3 years ago, there was this stuff that was floating around where it turned out that on MacBooks, the battery pack, the software inside that, or the firmware update, the battery firmware update was protected by a common password. That is, every MacBook that you bought had exactly the same password in the battery pack, and someone figured it out, and then he showed that you could download a new firmware, and that controls the charging process. And by compromising the charging process, you can cause a lot of damage, including fire and stuff like that. Okay, so so that's a side note, but point just wanted to make is that there is software running inside the battery, and those battery terminals are not simply VDD ground. There's kind of a rich set of stuff going on in there, which is doing all this estimation and stuff like that. Very crudely speaking, then basically what we are trying to do is that when you are trying to charge the battery, you want to make sure that the battery which has a lower capacity, if I overcharge it, dangerous thing will happen. So somehow, so I have to somehow kind of balance them out. So one thing that may happen is I'm only going to charge them up to the lower, weakest cell's capacity, but that is basically going to mean I have unused capacity left over in my battery pack. Or alternatively, I have some sort of smarter circuit which which basically kind of stops charging in one place and takes it over to the other place. So passive approaches, basically all they do is they stop the charging process the moment the weakest cell is filled. The active approaches basically kind of manage this process in a manner that you can sort of differentially charge and differentially discharge the different cells in the package. I'll not go into details. I don't expect to know them. What matters from the software side is that there is this battery management software which is running at the lowest level, which is looking at the load and then managing the battery pack based upon that. Okay, and that's kind of a bit of a control system. So it's an electronic system which manages this. It's typically, like I said, in the battery pack as part of the battery pack. So what you buy is an intelligent battery pack, and it basically monitors a whole bunch of aspects of the battery, including state of charge and state of health. In many cases, batteries have to be cooled. So electric vehicles, the battery packs are so huge that the cells which are deeper inside the battery get heated up quite a bit. So there's a whole cooling system, and that needs to be managed, and so on and so forth. So lithium-ion batteries, which we use in our laptops and all, they typically come with this kind of hardware software built in. Part of the reason is that if they were to not put it, then the process of charging and discharging these batteries can be pretty dangerous. I kind of cited some anecdotes the last time we had met about sort of incidents in my lab and all. So these were raw lithium things, but the stuff that you kind of buy, they have all the stuff built in so that they're kind of safer to use. They kind of manage, even if you try to be somewhat not very careful, kind of the BMS will sort of prevent you from doing that. So inside this BMS, there are a bunch of things that go on. The state of charge, state of health, you estimate those, you estimate kind of other parameters of the battery, and then you bring all of that to bear and then manage the process. So let's see, I'm going to skip these. Yeah, these are details. I'm going to skip several slides. Okay, so there is sort of when it comes to from a fuel gauge kind of thing, you can count how many ampere hour you have used. So current sensor plus the time of usage. So you're continually monitoring this stuff. And the other one is this open circuit voltage estimation. Okay, so this is where you're looking at the battery pack voltage. Now this one is a little bit tricky for the following perspective. You cannot look at the battery's voltage when it is in use. You have to look at its what is open circuit voltage. Those of you who are not E, that means I need to disconnect the battery and then measure its voltage. But obviously I can't do that if the battery is in use. So one way you could do this thing is if you have a multiple cells in the battery pack, you disconnect the cell, measure that while you're using the others. Otherwise, you'll have to do some sort of an estimation process in this. So Ampere-hour counting is basically sort of continually keep track of the current that is going on and the time. And then finally, the model-based that I had talked about, where you have some sort of battery model which you maintain in your algorithm, and then as you are using the battery, you kind of update that model and sort of work with that. So let's see, I want to jump to the part which is the more interesting thing for our purposes. So long story short, there's a lot of stuff going on in the batteries. What attracted, yeah, go ahead.
So is there any way to kind of measure open circuit voltage with other variables while the load is still connected, or is that?
You can estimate it through by maintaining a model where you will have open circuit voltage as a variable, but the only way you can measure the open circuit voltage is to disconnect a cell, measure it, bring it back to service. Okay. Yeah. And what I presented to you are the more classical textbookish kind of mechanisms. I think a lot of this stuff is also things which perhaps are somewhat more proprietary, the way kind of the Teslas and the Nissans and all kind of doing their EVs and all. When it comes to the kind of battery packs and all that we see in laptops and things like that, the more typical stuff, I mean, I think is the Coulomb counting, so kind of how much charge is going out, or Ampere-hour counting. So that's very commonly used because there is not much of a redundancy in these systems. So you do not have multiple batteries being switched in and out kind of thing. So you rely on these sort of things. The model-based stuff, where you have kind of an elaborate battery model and you update its parameters based upon how the battery is being used, is again more at EV tech level. I have not seen it when it comes to mobile devices. Now, what did happen though was that given all these effects and all that I'm talking about, when kind of sort of mobile devices, their battery lifetime and all kind of began to become an issue, there was effort which came up, could we come up with better battery models which are computationally friendly and yet can give us better results than what we saw previously. So we saw that Q-curve equation, right, that was kind of the most elaborate one we had. So in sort of the EECS side of things, several things kind of emerged. So one was that people said, maybe I can begin to model the state of the battery as some sort of a stochastic process. So I have states which represent different battery levels, some sort of perhaps a Markovian behavior, and then I kind of jump from them. Not very realistic. Another one which sort of comes more from people who do electrochemistry and all, that is we really go ahead and mimic the electrochemical processes in the battery. So there were several models like these floating around. The one which actually in my group in some research we used to use was something out of Berkeley, and that was a set of PDEs with, if I recall right, something like 70 or so parameters. So just not something that you can use for any realistic purposes, neither for simulation nor for state of charge maintenance and all. There are, from computer science perspective, there are two broad uses really for this technology, for a good battery model. One is to do this state of charge, state of health, these kind of things, state of charge. And the other one basically is during simulation. I have a program, I want to mimic it. We have models for processors and other than that. What's the equivalent thing for the battery? Could we have a more elaborate model? So this, the Berkeley model I'm referring to is this dual foil. So the idea was that the kind of work that people do is I do a software optimization and I want to see what's the impact on lifetime. Okay, so those are the kind of questions we want to be able to explore. You would certainly need a model of your system itself, the processor and the memory and stuff like that. We saw some of that in the prior lecture, that how you might model this thing. For example, when mobile phone emulators came out and also like both the Android and iOS side, they allow you to get an estimate of the energy consumption of the program. You can find hotspots in your code, rewrite them, do stuff with them. But as we saw, that if batteries matter, then you also have to mimic the battery. Otherwise, you're not getting the complete picture in terms of lifetime. So battery modeling became kind of some 15 years ago or so. Sort of there were some more effort sort of went in that, and the model which ended up getting the most traction in the CS community came out of a group at, I think it's Arizona State, or might be University of Arizona. And what these guys did was they did a very first order approximation of the physics of the battery, and then they showed that kind of the results are really quite good and all. So now the real battery, the underlying processes are very complicated. Like I said, the Berkeley electrochemical model, the dual foil one, is a whole bunch of parameters, not practical. So could we have something which is much simpler, hopefully, and yet is good enough for in terms of accuracy and all. So this model, which I kind of call as Ampere-hour model, this is the name of the first author, but the way it works is it basically says that, look, let's create a approximation of the battery. So inside the battery, if you may, conceptually, I have material, the charged particles, and then we use them as we use the battery. So they basically start out with saying that, look, I can think of one of the nodes of the battery, and inside the battery are charged particles, and essentially in a fully charged state, the whole thing is filled up. So this is like the bucket full of charges, and then the battery has some width. This is my x equal to 0. Okay, and then as I start drawing the power from the battery, then what I'm doing is I'm consuming these charges, and therefore there will be a depletion of the charges. Except the level of the charges, instead of falling uniformly, because these are charged particles which move sluggishly, it will have a profile which looks something like to the top right. And then let's say I stop using the battery for a while. Then again these things will even out, the concentration will even out, it will look something like this C. And then again I use it, and so on and so forth. Eventually at some point the concentration of the charges at this x equal to 0 will fall to 0 or some below some threshold, and at that point in time we'll say the thing is dead. So now there are lots of physical things and all which are being glossed over, but at a first level this kind of a one-dimensional diffusion model is a good representation of what might be happening inside the battery. And so region of width W, there's a concentration that we define, Cx of t, which is saying at time t, what at distance x, where x is from 0 to the width, what is the concentration. So that's the variable that is key to our equation. And what we're interested in is the concentration at x equal to 0, because once that falls below a certain level, that's what it matters. There is some initial concentration, C star, which we kind of just redefine in terms of some rho of t. And then what we're looking at it is that when C0t, concentration at the x equal to 0 point, if it falls below a cutoff level, then the battery is dead. Or another way of saying is that as I use the battery, at t equal to L, where L is the lifetime, would be the first time the Cx of C0 of t will become 0, okay, or will be less than a threshold. So now it turns out for one-dimensional diffusion, the equation is kind of something called Fick's laws, but it's a relatively simple equation, which basically says that the flux at time t at distance x, you can think of flux as the flow of charges, so that's current or current per unit area. So Jx of t looks like this, and the other equations like there are two coupled partial differential equations which exist, and you have a diffusion constant d which exists in this. So these two sets of equations. Now, if you recall your high school math or calculus, when solving these things, you also need to know the boundary condition. So the boundary condition in this particular case comes from a couple of things. One is that what is happening at x equal to 0, and the other is what is happening at what is happening at x equal to w. So one simplifying assumption they make is that the battery is so big that at x equal to w there is no current. Okay, so essentially there's nothing happening at that surface. And at the surface at x equal to 0, it is basically proportional to our current. So this term, the J term, really is proportional to current. So there's some additional stuff comes in, the area of the anode and all. So now we have these two equations. This one is valid at x equal to 0, and the other one is valid at x equal to w. Let's see, I seem to have a minor. Okay, so sorry. So we started out with those two equations. We attached the boundary condition. So now we have the area. So I ignore the other ones. I over A is the current per unit area. So that's the flux. There's some other constant terms out there. And turns out that this equation has a nice analytical solution, which kind of looks like this. So rho of t, if you recall, rho of t we had defined in terms of concentration C0 of t. So rho of t is representing 1 minus C0t over C star, and C star was the initial concentration. So initial concentration was C star, and so rho of t, we are saying what is the concentration at the electrode at time t. We would start out with C0 of t being C star. So initially rho of t would have been 0, and then kind of yeah.
Does this mean that thin and long batteries are better than thick and short batteries?
Thin and long batteries are better than. So firstly, remember, I mean, the W and all out here are the approximation. The only thing that matters is the area A. I don't know whether thin and long battery versus. I think, in fact, you probably care more about that which shape lets you pack most volume with the smallest area. So, and then the packing of those things, okay, inside the cell. That will probably dictate bigger um, factor in this.
What does W exactly mean?
W is the width of the battery, and we are basically saying that W is such that at the far end there is no flow of current. So my boundary condition could be 0. That's a mathematical simplification. So again, this is not what is happening in reality, because remember, in reality there is another, there is a cathode, there is an anode. The charges are moving between these two. So the real sort of physics is obviously far more complicated, which is what that dual foil stuff captures. This is making a very simple approximation. The other thing is looking at a cut, 1D. The real battery is 3D, so there's diffusion happening in multiple directions, and all of that is getting ignored. Turns out that this model works very well as in single-digit percentage points, which is pretty good for the kind of thing that we are after. So analytical solution ends up looking like this. There is a rho of t term in which you see these two terms. Now the first term, I of 0 to t, I of tau d tau. What is that? Current times time integral. So current over battery, integrate over time, 0 time. Right, but charge, what charge? It's a charge used by the load. Load is taking I of tau, so that's the energy being used up by the load. So what is the second term now? Now if you notice in the second term, I have a diffusion constant and all that's happening. So this second term corresponds to that I'm actually, there is a bigger depletion in the than what just the first term would have suggested. First term is what would have happened if the only thing I had to worry about was how much charge the load used. But the other component is basically saying because of these sluggishness in the battery, the diffusion process, it seems I have used more charge. Okay, so this is kind of like stuff which there's an artificial depletion at x equal to 0, and then if I let the battery relax, it will again even out. So rho of t kind of looks like this, is basically saying that the total charge that has come out of the battery seems to be the actual charge which I used plus this sort of non-ideal term. So now if I were to make some adjustments, we end up with this kind of a model. Basically says alpha is equal to from 0 to L, L being the lifetime. So in this particular case, we think in terms of lifetime. So the time at which the battery dies. So this is what the load would have used, and this is the part which corresponds to the non-idealities in the battery. And this is an infinite series over a whole bunch of terms, and those terms relate back to data, which again relates to diffusion constant. So this is kind of representing diffusion constant terms. If I did not have those non-idealities, in the second term will go to 0, and I will basically be left with an ideal battery model, which is charge drawn from the battery is the current over the lifetime.
So the second term in the non-idealities means the recovery process, which happens due to
It also captures a recovery process, absolutely. So what does recovery process mean? Recovery process means that somewhere along the way, I of tau became 0. But the diffusion process will continue. So it will put the charges back there, and then so if you have a profile which I of tau is not constant, but I of tau kind of goes up and down, this actually does capture the recovery process. Okay. So this captures the effect of the rate capacity effect, namely higher the current, the lower the capacity, because higher the current, guess what? The second term goes up. So for the same amount of material in the battery, I would be able to operate for a smaller, shorter amount of time. okay, because some of it will go towards that, more of it will go towards that. If I'm doing a high current, so it captures both those effects. So the nice thing out here is that this whole thing, how many parameters are there? In this battery model, there's alpha and there's beta, two terms. That's it. L is our desired lifetime, and M is just a initial index out here, right? So I've basically taken all of that stuff and we've reduced it down to a battery model which has this exactly two parameters. Our models previously, like Pucher's model also had two parameters, if you recall. It had the Pucher's coefficient and it had the capacity of the battery. Okay, so in that sense we are very similar. Also has a nice thing that if I were to ignore beta is then the first term corresponds to an ideal battery. So it has certain elegance to it. So a battery with two parameters, it boils down to how do I estimate? So if I now, one of the things is, remember again, we have an infinite m equal to 1 through infinity term out here. So in practical setting, you have to compute only up to a certain point. And the other thing is, could I do this thing efficiently? Because as in, if you think in a simulation setting term, or let's say you're using this model to worry about state of charge, every delta time step, you know how much current was used in the recent delta time step, and you want to advance your integration by one step, okay, or you want to project it out. If I were to give you a waveform that the load is going to take, using this, you can predict what the lifetime is going to be. So those kind of things you can do. So right-hand side represents the capacity of the battery, and the first term is the total charge consumed by the system, and the second one is that the charge which we could not use because of the non-idealities. As beta increases, if beta goes to infinity, the second term will go to 0. So essentially an ideal battery is one where beta is very large, okay? And large beta basically means diffusion is very rapid. So essentially we begin to approximate ideal battery. So now when it comes to using this model in reality, so what you do is your task is to measure, to estimate alpha and beta. So what you do is you subject the battery to a whole bunch of constant current loads. So you basically take the battery, hook it up with a current source, and then let the battery run down, okay, and see how long it lasted. Do it for a different current. Again, let the battery run down. So you're going to have a bunch of parameters which will give you particular constant current and the corresponding L, namely when the battery died. And then your goal is to estimate a value of alpha and beta such that your measured current and the predicted that you basically do a electron non-minimization. So that's kind of a strategy. It's a simple sort of, if you have access to MATLAB, you can kind of calculate it easily. So that's how this model gets used. The other things that have happened is, if you read kind of the original papers and papers it followed, it's a very well cited paper. People have looked at all sorts of things. How can I compute this thing efficiently? How do we handle that 1 to infinity terms? Obviously, you don't go to infinity, compute it up to some level. Then looked at certain waveforms which have certain properties, like what happens if my waveform is duty cycles, like I operate at a peak load for some time, go down to 0, those kind of things. So there's a lot of mathematical sort of simplifications and all which sort of you could bring to bear to compute it efficiently, so that you are not resolving the whole thing, but rather you advance time a little bit, see how much it's changing, and also how many terms you have to use as you increase m. As you increase m, since m it appears out here, so as m becomes larger, this term becomes smaller. So in our series, the terms are decaying. So I don't have to look at all the terms. I look at the first few, and that will give us a numerically acceptable approximation. So this is, I want to just present this thing as an example of the kind of models that emerged when computer scientists looked at this problem. Okay, before that, I mean, the battery community was into these PDEs and all, and the early attempts from EECS were very simplistic models, Markov chain and all, which were more bogus than Buchert in a way. So this was pretty good in that regard. Let's see. I unfortunately don't have a slide, but in the paper they show a table where they kind of, this is sort of early 2000s, where they worked with PDAs and all of that era, and they kind of showed that the results kind of, they were able to model the state of charge in the battery and the lifetime and all with pretty good accuracy. Okay, things which for all practical purposes were quite sufficient for our needs. Now, what I don't know is, like for example, when Apple uses, tells me so much charge remaining and all, whether they're actually using any of this fancier battery methods. I suspect not. I think what they're probably using is a simple charge estimation. Where I do see these models is that there are MATLAB toolkits and all with more realistic battery models, and you would find this kind of stuff in there. There is other stuff which goes on there as well, modeling other characteristics of the battery, like what is internal resistances and all. One thing this model does not, well, two main things that this model does not do. One is it does not model the voltage. Okay, there is only focuses on the current. It's assuming that the voltage being output by the battery is constant. In reality, as the charge decays, as the concentration changes a thing, there is a decay in the voltage. I did see a subsequent paper by the same first author where they did seek to model the voltage. And the second thing is it doesn't model the recharging process. So this is for a battery which was charged up and I'm using it. What happens if I inject charge back into the battery, and how does it impact? I guess one could argue that perhaps a diffusion process will run in reverse, but I have not seen anything. So that's where, so now with what I have sort of talked about, we can model the digital computing part, we can model the radio part, and we can model the battery part. So at least in principle now, you can model the entire hardware substrate, and now you can sit on top of it. The nice thing in this framework was we had very few models to worry about. When we modeled the digital part, if you recall, there were, I think, 5 or 6 parameters eventually. When we modeled the radio, there were 3 parameters, 2 for transmit and 1 for, well, actually 4. There was a distance coefficient one. So the point is, in all these cases, we are ending up with fairly simple set of parameters. You can take sort of a complicated system and can do fairly effective modeling, which works well enough in practice for one to use them. Some other sort of notes: fuel cells is something which has always been kind of talked about a lot, and fuel cells are not batteries, but instead kind of the concept is that when it runs out, you put in a new vial of fuel, and the fuel in this case is some source of hydrogen, and kind of the idea is that you let's see, I have a figure. So the idea is that you combine hydrogen with a source of oxygen, and then the outcome is water plus kind of this current which is flowing. So fuel cells, the big plus is that the fuel itself is a source of hydrogen. So if I have any sort of thing where I can pack a lot of hydrogen, then I have a very high energy density that exists. So people have looked into all sort of ways to kind of do it. Obviously, if you could store liquid hydrogen, that's the ultimate. But there are a whole bunch of other things you could do, hydrogen trapped in nanofibers and stuff like that. It's been one of those technologies which never really caught on mobile type devices for a variety of reasons. There are these things available for you as battery, as whatever power supplies for use at home and all in the emergency settings. Toyota right now is pushing a car very heavily. I forget the name. Mirai, yeah, it looks really ugly. Right, that's the car. And there are whatever other trucks and all these kind of things which are government agencies buy and all. Okay, the big problem with these is the supply infrastructure. Electricity is always everywhere there. Electricity is there. gasoline infrastructure is there, but the hydrogen delivery thing is not there, even though Toyota is promising, 3 years of free fuel supply and stuff like that. Yeah.
So they're on that table. You have watt hours per kg and per meter.
Mm-hmm.
How much more dense does the hydrogen and graphite nanofibers make in water? Like, does that significantly add weight to the battery?
Or how much would it add to the weight?
Yeah, because
I mean,
like, does that increase the water's density and stuff as well? Or?
no. So it's basically looking at the overall weight of the whole thing, right? I mean, it's not just the weight of the hydrogen.
Okay.
Right? So it's taking into account the weight of whatever thing it is embedded in. So yeah, I mean, this can be pretty dense. I mean, you can just trap a lot of stuff and all out there. Point being, basically, even at the low end, it is far ahead of what regular batteries see. Okay, so in terms of the fuel, in terms of energy density, whether volumetric or mass-based, it's pretty good. But I think it just remains one of those things which, for electronics, really hasn't caught on. For EVs, there is a big debate going on that front. Okay, whether the lithium battery pack based stuff versus the fuel cell based stuff. And I think ultimately they're both electric vehicles. Just remember that. I mean, at the end, there are motors in both cases. In case of fuel cell, the fuel cell is used to then generate electricity, which then drives the motors. The difference really is in the energy supply mechanism. Okay, in one case, fuel is being supplied to some central power plant. We are distributing electricity. Electricity is being delivered to your car. You're storing it in lithium-ion pack. In the other case, we are sending effectively fuel to the car and then generating things locally. So they're just kind of different takes at it. From what I understand, at this stage, Toyota is very much in favor of this naturally, as are the public statements from a lot of the big car vendors. On the other hand, Tesla and Nissan and a few of these companies, they have sort of gone after the lithium-ion route. From what I read and all, I mean, just because of the logistics of the infrastructure and all, the latter will likely succeed. But there is one thing in favor of hydrogen, which is it can be refueled very rapidly. One of the issues with with plug-in electric vehicles is that you need they charge slowly on the standard outlet, and those high-powered DC chargers, as they are called, they still take like half an hour or so to kind of recharge, so significantly more than just refueling. So fuel cells kind of remain attractive possibly. Fuel cells are being used in data centers as well. There has been at least some papers and a lot of Microsoft that I've seen in this regard, kind of talking about that. Essentially, by integrating fuel cells in a data center, kind of the idea is that you can provide increased availability. So one of the issues that happens is that there are rapid changes in the overall energy consumption that a data center sees. So this fuel cells kind of provide that buffering energy. So that's one place where fuel cells are being used. The final thing I want to mention is that we talked a lot about batteries. One of the things that also is part of the power supply system, very important, but sort of I'm ignoring it. And I don't know whether the course at UCLA covers it, which is between the battery and the load is also this DC to DC regulator, which takes the voltage coming out of the battery or the power source and then creates a clean voltage for the load. The problem, the reason this matters is there is loss within that also. It's an analog circuit, there is some level of efficiency, there will be some regime in which it's very efficient. A lot of work has happened in improving these efficiencies and all, but nevertheless it remains sort of an extra load. I have seen therefore work where people decide to eliminate it. So kind of the idea is that I operate my circuits directly off the battery and then take the risk. So you may have brownouts happening and things like that. You may see corrupted voltages and all. but you do not have to pay this extra degree of translation. So that's a topic in itself, kind of more circuity in nature. So take away from this lecture, this set of slides really is that batteries have non-annualities, that they matter. There are two levels of interaction between software and battery. One is that you need to manage the battery, and the other is that you can manage the load so that we make more effective use of the battery. And so the former is done by the battery management system, and the latter is done by whatever your protocol or operating system scheduling and all. And I guess the other point is that there are fairly reasonable battery models that exist. So when you are sort of evaluating the system and all, there is no reason not to use those. Okay. The part which you miss is that you need to learn those parameters. So for real devices and all, I mean, as you could see that for that simple Rakamatov model, at the end we were left with two parameters, and a bunch of experiments could easily yield those values for you. So, but the place where batteries really become complicated are these bigger systems, EVs and stuff like that, where sort of the battery packs are pretty elaborate. You have also thermal issues and those kind of stuff which come in. But as we saw that, I mean, the battery issues have begun to at least gain some visibility even with our smartphone type devices and all. Okay, so there's a fair bit of stuff. And final bit, I guess I haven't sort of really talked much about it, which is battery awareness, which is can occur in a variety of ways. One part which I didn't go much into is the charging process. So when you charge the battery, there are many different ways you can charge the battery, but very crudely speaking, when you charge the battery, there are two phases that you go through. There is a constant current phase and there is a constant voltage phase. Okay, and what happens is you initially charge the battery in one regime and then you charge the battery in a different regime. So the way people have been exploiting these kind of things is, firstly, I want, oftentimes our goal is, I'm willing to sacrifice the health of the battery as long as I can get to a certain charge level very quickly. So you have seen emergence of rapid charging in smartphones in past couple of years or so. The second thing is, could I be smarter about scheduling workloads? So I have seen academic papers and patents from companies like Apple and all, which kind of go along these lines that, I know that whenever you are at home, you charge the battery. So if there is some workload which is deferrable, like let's say an app update or stuff like that, perhaps that could be deferred. So they look at your location and all and kind of begin to use that in this process. Also, certain workloads, maybe they can be done when the battery is being charged. Even more so, perhaps it can be done in the right regime when it is charging. All with the goal of not so much minimizing energy consumption, but I think the more interesting metric is availability, which is I want to give the user the illusion that the phone is ready to do whatever he or she wants to do whenever he or she wants to do. Okay, it's matching the energy supply process with the user's computational communication needs. That's really your goal. Okay, everything else is a proxy.
How normal is it at the moment for phones to be able to, when you plug it into the wall supply, use that to power the phone and then simultaneously charging the battery? Is there any work being done on that?
So it depends. There are workloads that you can currently do on a phone where that won't happen. Okay, that is pretty much everything is needed by the processor. In fact, there are workloads that you can do on the phone where if your battery was not there and you only had the wall outlet, you won't be able to do that. Okay, at least certainly not with the older generation Ampere USB 2.0 type chargers, because they were severely, like USB 2.0 was limited to half a amp thing. Then you began to see Apple introduced first this higher current version, and the way they did it was that basically they created chargers which could supply a higher current, and they had some sort of an analog trick so that their phone will recognize that the charger was capable, and that's how it would work. Then Samsung soon follow with their own proprietary thing. So you would often see these chargers. From 3-4 years ago, you would see these chargers like this is for Apple and this is for Android, and they were both kind of pushing the current to 1.5 ampere or 2 ampere, but they were using some proprietary methods to kind of do it, and they were sort of just the fragmentation in the market that happened. I guess to answer your question, if you have the higher power charger, then certainly you could do both. Supply the charge the battery and do the load. If you have a wimpier charger, then that may not be possible, and then you have to kind of figure out what is possible. Okay, so yeah.
Would the software on the phone actually be able to recognize that, or would it just try and do that load and figure out, oh, I can't do it?
Oh, it can. I mean, you can basically So on this front, I mean, I know on Android you certainly can. You can have visibility into is the phone plugged in, and what is the capability of the adapter you have plugged in? As in, are you charging at a higher rate or a lower rate? So you certainly can, and then by further interacting with the charger, you can do games like within that charging phase. As you're shifting from constant current to constant voltage, this kind of the charging profile, you can begin to make sort of changes on that, but that would require a degree of cooperation that does not exist. I think 4 years ago, one of the course projects out here, they had looked into that. A nice paper published out of that, where basically what those students did was they basically decided where in the charging process can I shift the workload to. And it depends upon also individuals' usage habits, what kind of charger they use, adapter they use, and all. But there are opportunities there. If I recall the results right, there, I mean, there was non-trivial gains like 20-25% increase in availability or being able to use the phone. So there are interesting possibilities that exist there. Location-based battery management or whatever. Using location as a proxy as to when your phone is likely going to be charged, and then using that to defer loads. So as a scheduler for the OS, what you have control over is when something gets done. And not all workload is non-shiftable. Many of the workloads are shiftable because they happen in the background. They correspond to updates for some apps or stuff like that, and or syncing that is happening, So there is some of that can happen. Android actually provides a nice framework for syncing, and another project in this course a couple of years ago, what those students had done was they created a system where application can issue communication requests, syncing requests and all, but they could attach attributes to it, basically saying, this needs to go now, or that this is deferrable. So you can basically begin to create a system where now you're giving enough hints to the OS, and that it then can use to decide or prioritize things. So some of the workload will happen only when under certain conditions are met, like batteries at a certain level, you are plugged in, stuff like that. Those kind of conditions can be in place. So because many workloads are delay tolerant. I mean, for example, I could care less if, for example, I don't know, I use Runkeeper for my workout, and if it doesn't make it to Runkeeper's website a few hours later, probably no big deal. Okay, so there are lots of examples of such workloads which one could leverage. So battery awareness is important, and I guess the related point I'm making is that it's not so much about how much energy am I using in this case, but it's really about giving users the impression as if the battery never runs out. Okay, but we are doing it by careful shifting of the workload. Okay, let's take a 5-minute break. Okay, let's restart. So now that we have modeled the systems, I guess at least some of the key components, next thing is what can we do to manage them appropriately. And this could obviously be done at many different levels, but we'll start in this one on focusing on kind of the low levels of the computing system, and specifically with the goal of minimizing power or energy. Okay, so there could be a variety of related goals out there. One is I just want to keep the power consumption low. Now that goal in itself doesn't make much sense, because if you don't give me any other constraint, I will not do anything, right? So it has to be keep the power consumption low while meeting some temporal goal, okay, or more generally maintaining some certain level of quality of service, if you may. Another alternative goal could be I want to minimize the energy consumption to do a certain task. So in that case, again, if you do not put any bounds on it, then I could say that I am going to do it so slowly that it will take infinite time. So again, the problems that the proper way of framing these things will always be there will be some optimization variable, and then there will be a bunch of constraints. But without that, kind of these problems won't make much sense. But what we're going to look into is like what are the different ways historically, and by history I mean this area kind of starting around mid 90s, a flurry of work which continues to this date. Okay, so roughly 20 years. And what happens is technology moves, and then the people move, sort of come up with different set of techniques, and a whole bunch of stuff has been happening. So what I'm describing is really kind of the first era of that work, and not the more recent one, which I'll cover in a later lecture. So going back to this equation that we have seen before, if I just focus on the digital systems part of it, there were these three very broad components that we had. The dynamic power, or kind of the switching power, that was the first term. The second term was the stuff that was happening when you were switching again, but for a transient period of time, leakage stuff, and then others, which is happening all the time. Okay, so and we had developed some models and all based upon that. What these so there are different regimes out here that sort of matter. So firstly, if leakage dominates, that is this I leak dot v, that term dominates, then that's basically kind of argues for that you should do things as quickly as possible, because as long as my system is up, whether I'm doing anything or not, this is going to be there. So my goal really has to be in that case to run as quickly as possible. On the other hand, if the first term dominates, then and which it used to, then my considerations are going to be different, because now there seems to be some interesting sort of tension between voltage and frequency. To first order, frequency has some relationship with voltage, which is upwards, that is higher the frequency, sustain a higher frequency, I need a higher voltage. So there is the dependence on voltage is pretty strong. So what this boils down to is, if I look at this term, the active term, then now I can have different kind of workloads. And very broadly speaking, there are workloads where we care about throughput. These are transactional workloads, as in I have a series of transactions coming in, and I want to process them as quickly as possible. It could be database transactions, it could be samples of a video stream or audio stream, and I want to just focus on keeping up with them. And to the first order, I don't care about the latency. That is, even in the worst case, my latency is so quick that it doesn't really matter. Latency is so short that it doesn't really matter. In that particular case, if only throughput is important, then what I could do is, the game I can play is intuitively staring at that equation. I can reduce the voltage, but since power reduces very dramatically with voltage because of the quadratic dependence which exists there, and actually more because of the frequency, reduced voltage, reduced frequency, but then you make up for it by some other means. For example, by having concurrent hardware. Okay, so this works great for or pipeline hardware. So this works great for a lot of domains where throughput is what you care about. Signal processing tends to be a great example of it, but anytime you have time series data that you are just you have an operator working on a time series data, you're continually processing it. This works great. Then there are workloads where we care about latency. That is, the task arrives and I have to do it, and I have to do it within a certain deadline. So now we are into the latency critical realm. Those of you who are in my 202A, you sort of spent a lot of time looking at deadlines. So in this particular case, really sort of our workload is of the nature, an event arrives, I process it, done, I wait for the next event. And in that particular case, intuitively, if you may, our best strategy is going to be that I shut the system down in between and then have some mechanism that when the task arrives, I'm rapidly able to wake up. And then finally, supporting both of these, there is obviously the third aspect, which is I can improve all those constants, the alphas and the C's and all, okay? And that's another way of saying is that I basically create more efficient algorithms, more efficient hardware. Efficient algorithms will switch less. Efficient algorithms will perhaps require less hardware, so C will be less. If I'm a smarter circuit designer, I can make C less, and so on and so forth. So a combination of better hardware and better software design can lead to alpha and C being small. But when it comes to V and F component, really kind of these two regimes that we are after. So continuous streams of samples or streams of events coming in versus asynchronous events coming in, and I'm reacting to those. And they're kind of different regimes. Now, I may have workloads which are systems where I have a combination of the two, then obviously things get muddied, but in a pure sense, these represent things that you see. There is a third category, which is I don't care. I mean, do the best effort, which is what much of general purpose computing is about, which is I give a task to the OS, I don't specify anything as to, but there's a certain loose expectation that it will do the right thing, but I don't tell the operating system that I want to have this throughput or I want to have this latency. So that's the best effort category. So let's look at these. The part I want to focus on first is kind of really the left regime. And the reason I'm focusing on that is because that is where the early work happened. In terms of where it, so sort of going back to the early days of mobile computing and all, which is basically early 90s, at that time, a lot of the bottleneck was, when it came to power, was indeed in the workload of this type, because the signal processing part, the communication, these things dominated. Even to this date, radios and all dominate for a bit, but those days even more so. So the ready low-hanging fruits were, could we do something about those? The other part was this was also an easier problem, and we'll see sort of how it works out. So now I have kind of this intuitive motivation out here that can I reduce voltage, gain on power, but compensate for it by means of a better architecture or a more concurrent algorithm. So I'm just going to walk you through the intuition. I'm going to present it in terms of circuits, but it's equally applicable for software running on processors and so on and so forth. Okay, but just wanted to get the intuition out of the way. So the argument behind this thing is I reduce the voltage. When I reduce the voltage, my circuit can only run at a reduced speed. So it's lower voltage at a lower clock rate. So now what I do is I basically play some games to recoup that loss of speed. So if I were to give you a piece of hardware and then I suddenly tell you that its clock frequency is now half of what it was, then there are a couple of things you can do. You can use two of them, or you can pipeline it. Okay, these are the two ways we are always taught to kind of do things. Or third option is I can try to figure out is there a better way of doing that task which takes half the time. Okay, that's half the instructions. That's the third thing. So basically, we're going to play that game, and while I'm going to talk about CPU, essentially the concept works for any system where you can find an alternative way of doing it. What we are really doing out here is we're trading off power with area, as we will see shortly. So let's look at an example. On the left-hand side, what we have is for some circuit technology, an old one, but kind of intuitively what it's showing is as I reduce the supply voltage, the circuit delays go up, which directly means that the clock speed goes down. So as I come closer and closer to the threshold voltage, this is an old technology, so the threshold voltage was somewhere 1 plus. Point is delays go up. So the maximum frequency at which my processor can run goes down as the supply voltage is lowered, and there is this kind of a behavior. Separately, from a computer architecture perspective, if I have parallel multiple processor cores, let's say, then as I increase the number of cores available to my system, then I will see some speed up. Hopefully, I'll see a linear speed up, but generally speaking, after a short while, we begin to taper off because you have communication cost. Your algorithm may not be entirely parallelizable. There is this well-known thing called Ampere-hour law. Anyone heard of it? What is it?
As you increase the number of cores, the speed up is not exactly 10, but it's rather.
And why is that? Like, what, in case of Ampere-hour law, what is the reason?
Only a fraction of the whole program will be spread out. So
Yeah.
the
So
remaining will obviously take the normal time.
if I start a program, half of it is parallelizable, the other half is not. Even if I parallelize the health of the first part, the other part becomes a bottleneck, right? So that's the interesting. The point is always I want to see some tapering off or even going down. Why do you think that happens? I increase the parallelism and I see a slowdown.
Maybe the overhang of parallelism was more than the message.
Communication cost.
Yeah.
That begins with the point. Okay, so our curves look like that. But what I can now you can see is the following. I can begin to do some compensation out here. So what I could do is I can increase the parallelism. I get some speed up. So let's say I do a parallelism of, let's say, 3. Looking at this curve, a parallelism of 3 corresponds to a speed up of 3. Going back out here, since I have a parallelism of 3, so I can afford for the same level of performance a slowdown of 3. And therefore my voltage can go down from 3 volt to perhaps something like 1.7 or so. And that 1.7 is going to give me a 1.7 square improvement, right? But I'm using 3 out here, and so you kind of put all of these together. I'll show shortly. The numbers work out in your favor. Okay, so that's the main argument out here. So we are going to show it with a very simple kind of an example. I have some computation going on where I have streams of data samples coming on A, B, and C, and I'm adding A and B and then comparing with C. So like if I look at a tuple, I have A, B, and C arriving, and at every time step I do A plus B is it greater than or less than or equal to C. Okay, and I output the result. And all I really care about is keeping up with it. And let's imagine, for the sake of argument, that addition take 25 nanoseconds. Sorry, addition plus comparison took 25 nanoseconds. So with this design, I can every 25 nanosecond I can take a new value. Okay, so that's my baseline system. So I can run this thing therefore at 40 megahertz. At a 40 megahertz sample rate, I can process these samples, these tuples that are coming in. And let's say this system had some amount of capacitance that is equivalent to it. Okay, so for purposes of our alpha CV squared f, let's say alpha C corresponds to some value out here. And I start out with a reference voltage, some particular voltage, and I will have therefore some power consumption for the sake of power. Then what I do is I parallelize. So I go to a parallelism of 2. So I create 2 copies of my little specialized processor, and those tuples that are arriving, I set odd one to top, even number to bottom, and so they are working in parallel, and then at the end I have some sort of a switch multiplexer so that I know which one to select. So my output stream looks unchanged, but what's happening is that one is going up, one is going down, and since I have parallelism, therefore for each one of those samples, I can process them half as slowly because I have 2 of them going on in parallel. So therefore, the clock rate can be reduced by a factor of 2. So instead of operating the system at 40 megahertz as I previously was, I could operate this thing at 20 megahertz and still get the same throughput for processing my incoming data. In this particular case, I have some overhead, and generally speaking, my overhead in terms of that switched capacitance is going to be more than factor of 2 because I'll have to pay the overhead of coordinating these switches and demultiplexers and all. So let's say in this particular case, on design, it's 2.15 times the original capacitance instead of 2 times the original capacitance. But since I gained I need to only operate at 20 megahertz, I can lower the voltage, and it turns out I can lower the voltage by a factor of 1.7, going back to the previous slide. You multiply all of this together, you get that the new power is 0.36 Pref. So I have reduced the power consumption by a factor of 3. I have increased the area somewhat more than factor of 2. My throughput is the same, and my latency has gone up. Every sample now needs twice the time to get processed. So that's the trade-off that's happening. So I'm basically playing in the space of latency, throughput, area, power. And this is a design at a different corner in that space. While I presented it in terms of these, but this could be processor cores. Okay, I have transactions coming in. I send, instead of all of them going to the same processor core, I'm sending one to one, the next one to the other, and letting them work in parallel. If I have this type of parallelism, then that's great. If I can do very efficient parallelization even later, I mean, the closer this thing is to 2, the better off I am. But as you can see, that gives a reasonable sort of gain out there. The other way we are taught of making things faster is pipelining. So I can do the same thing out here also. So my tuple had 2 operations being done, right? On it, we were doing the addition and then we were doing the comparison. So what if we were to pipeline them away? So now I take my hardware and then kind of create these 2 pipeline stages, okay? So while one set of tuple is being added, the previous tuple which came is something, it is undergoing its comparison operation. So in this particular case, I need to sustain the same frequency. So my new frequency is going to be the original reference frequency. I still need to take stuff at 40 megahertz. But I still have a single copy of the hardware, but I have to pay some cost for this pipelining. So let's say my switched capacitance goes up. But since each stage has half the delay, I'm assuming that the 2 operations took equal amount of time. So now I need previously addition plus comparison needed to be done in 25 nanoseconds. Now each one individually needs to be done in 25 nanoseconds because they correspond to a single stage, and therefore again I can reduce the voltage, I multiply everything out, a similar gain happens. Now in this particular case, what happened? My area is kind of the same, let's say to the first order. My throughput is the same. My latency has gone up because each tuple will go through 2 pipeline stages, and the delay through a pipeline stage is, each pipeline stage is what it used to be the whole system before. So my delay has gone up, my area went up a little bit, my power went down a lot, and throughput remained the same. Okay, so again, appears to be a win. We are losing on latency in either case. I'm operating on a slower hardware, and therefore I'm taking a hit on latency, but I'm able to keep up with the throughput. For the kind of applications we are talking about, signal processing and all, these kind of latencies increases are relatively tiny because we are talking about a video frame which was previously we were processing every 30 milliseconds, now we are processing every 60 milliseconds. Or previously a speech frame we were operating every 10 milliseconds, now we are doing it at 20 milliseconds, those kind of things. Relative to overall application, this is a tiny increase in delay in some component in there. So often very tolerable. So by playing this kind of a game, I can easily kind of do this stuff. Big motivation. This was a big way by multi-core processors with voltage frequency scaling kind of are used effectively. That is, if you have workload that can be parallelized in this manner, then the first strategy, not this one, not pipelining, but this one, can be used quite effectively. So you are better off using multiple cores at a lower frequency voltage setting than a single core running at a faster setting, and by using this kind of strategy. So I'm basically using a combination of architecture, algorithm, and playing with voltage and frequency to kind of operate at a better point. You can combine these strategies. So I can have parallelism and pipelining both. And if you do that, in this case, you go even better and you have a factor of 5 gain in power. Okay. Again, throughput remains the same, latency goes up, area goes up. That's the combination that's happening. So this kind of architecture power trade-off is pretty routinely used. Chip designers use it a lot, but like I said, it's the same story with multi-core processors also. Going back to our original figure where I had said that I had two plots, the speed up plot and the parallelization plot, you can merge them together, you end up with something curve which looks like this. As I increase the number of processors, my power goes down, power for doing the same thing and the same throughput. But at some point it stops improving, and then if you keep increasing the processor, it might even begin to go up. Now, the missing ingredient in the story, which I kept silent on, is I ignored the leakage. I basically said, we're just focusing on the dynamic or the switched power component. If we also had leakage, then of course the story gets more complicated, because as I'm increasing the stuff, then that's adding a constant term, which we are not benefiting from the speed up and all. Okay. In fact, to the contrary, there by increasing the latency, I'm actually making things matters worse from that perspective. So once leakage comes into play, you may have to be less aggressive about this strategy. So that's the kind of the high order sort of intuition that one can imagine. So let's look at now sort of what kind of thing you can do. Oh, question? Yeah.
Is there any kind of algorithm or implementation which turns off codes if there is not enough work to do? Like
yeah, so I'm actually coming to the shutdown shortly. But obviously, if you have nothing to do, you should shut down. Unless shutting down and waking up unless you will be forced to wake up quickly enough that you might have been better off not shutting down. Okay, and the reason has to do with it because shutting down and waking up takes extra energy. Particularly for many systems, while you are transitioning from shutdown to wake up, or you actually consume higher amount of power during that period than you might not. Can you think of some examples? Some systems that you see where as you transition from whatever idle or stopped state to fully running state, you actually consume more power during the period while transitioning, as opposed to if you have just stayed up doing the full.
Light.
Huh?
Light.
Why for light? I never thought of light that way. Is that the case?
Well, I guess I don't know about U.S., but in China, classroom with those kind of lights, they never turn it off because if you turn it off and turn it on, the process, because those are gas inside, right? So the voltage to energize the gas for them to emit light is even higher than keeping them on for the whole night.
Interesting. I didn't know about that. So okay, yeah, I can. Okay, something that I would know.
Switching,
Huh?
turning on the engine of the car.
Okay, engine of the car. Yeah, that's because you are working against static friction and all. Yeah.
But they do it all the time now, right? They engine power off.
Yeah, so I think they have probably begun to address these things. So they shut off certain some cylinders and not the others. So those kind of things are happening. Yeah, hard drives is another one. If you monitor the current consumption of the hard drive, it is much higher while it is spinning up than if it is remaining to spin versus just remain shut down. Also, actually, when you start a circuit, the capacitors and all need to charge up. So again, there is a current spike when things are charging up before it stabilizes. So a lot of systems exhibit that characteristic. Okay. So any other question? So I presented this idea again kind of with the hardware with a static sense, but hopefully you can kind of make the connection that basically the same story applies whether it's software running on processors, and you can indeed play this game at runtime also. But let's move to runtime more explicitly. So when it comes to actions that you can do at runtime, there really are two very broad strategies that basically make sense. One is we can decide to shut down the system. And I'm using the term shutdown in a very loose sense out there because there are many degrees of shutdown, shutting a system down. But let's imagine I had a binary choice. I can run the system or I can shut it down. So this can be applied obviously to the whole system or can be applied to a part of a system. So I can shut off a display or a radio, or I can shut off the whole computer. Also, the thing is that there are typically components and multiple power states. So it's not simply component is up or down, but rather there could be a lot of intermediate states possible with different performance versus power characteristics that exist between those things. So are running in multiple shutdown states. So for example, very common in CPUs that they will say, I have a running state, and by the way, I have a whole bunch of shutdown states. They have names like doze and shutdown and idle and stuff like that, but they basically refer to what parts of the CPU were shut down. In some cases, like, is the clock running? Is the cache hot? Is the power supply cut off? All those kind of things. So there's a whole spectrum of states where the CPU is no longer running, but we have shut down some parts of it, but not necessarily all of them. So CPU can simply stop issuing the instructions. It can turn off the clock circuitry. It can remove power from different parts of the CPU and so on and so forth. So deeper shutdown states save more energy because more of the hardware is shut down, but they also take longer to restart. Because again, first you need to kind of restore the state before you can resume the functionality. This stuff is referred to as dynamic power management. That's the name under which sort of a lot of research in this space and all has happened. And the other technique is kind of a runtime variant of what we just discussed, which is scaling the performance. Okay, and what we mean by that out here is that a component offers us many choices of. So it's operating. It's doing the same function, but it's giving me different choices between the speed, and you can use the term speed in, let's say, throughput, for example, versus power. So, for example, I can have a CPU operate at multiple different power and clock frequency levels, which will imply power, clock frequency, and the voltage would be the norm out there. So this decision whether to shut the thing down or not depends upon whether I have something to do or not. Whereas the decision as to what performance level to run a component at is going to depend upon how much work do I need to do, what's the rate at which I need to do. So some combination of my timing constraints and what I need to do. These are called as performance states of a component. Okay, so it is working, it's doing the functionality, but it's giving us different timing characteristics. So I can dynamically scale frequency, I can dynamically scale voltage and frequency, I can imagine other kind of things. I can change the pixel resolution of a display, I can change the speed of a radio, I can change the RPM of a hard drive, these kind of things, as you can imagine, that kind of fall into that category, that there is some sort of a performance versus performance trade-off versus power trade-off that we can do. So it was introduced first in CPUs, but sort of really in a general concept that I can deploy. So at some level, I think any power strategy really kind of power management strategy really falls into one of these two categories. I mean, I really can't think of anything else. That I can either kind of do this kind of scaling game, or I can basically shut things down. And in general, you may very well have to combine the two. My first order might be to play the scaling game, and then when I have nothing to do, I shut down. So that's the those are two high-level knobs that I have. And then, as I mentioned at the start of this sort of slide set, I have to frame my optimization problem carefully, because if you were to simply tell me minimize power or minimize energy, then that leads to ridiculous solutions, because minimizing power means I will do nothing, minimizing energy means that I will take infinite time to do the task. Okay, neither one of them kind of makes much sense. So you have to frame the question properly. So there has to be something like some measure of performance is maintained. So like for example, throughput must be met or deadlines are still met or something like that. So basically I need to make use of those two knobs to optimize energy consumption for doing a task while maintaining those constraints. So for if you are into, let's say you're a Google running your search engine or web services and all, then throughput is probably the more important metric. I should be able to sustain the request that hit me. If on the other hand, let's say I am optimizing the running of the browser on the client side, then latency is the issue, right? I mean, the user clicks a button and the perceptual quality or the user expectation really is going to be measured in terms of the response time. How rapidly did my page load in response to that event? So depending upon which side you are, if you are kind of at the edge, very likely latency might matter. If you're at the center, very likely throughput is going to matter. Sometimes it's both. If you are in AT&T, you want to maintain throughput in terms of how much data you are sending through and all, but then you're also making promises on the latency, so you have to kind of meet those. So, and the final thing is that life would be very easy if these characteristics were static. In reality, they are not. So, essentially, the demand can change. So, I generally speaking would need to have strategies which can kind of ride along with the changing demand. And other kind of constraints might be there. For example, instantaneous power should never exceed some limit. Temperature should not exceed certain limit. Those kind of additional constraints might be there. So what we at the end of the day we really have is a control problem. I have given two knobs. I can scale the system. I can shut it down. I'm given temporal characteristics with it, and I have something about the workload, and I want to bring all of this together into some sort of a runtime strategy which optimizes something and constrains something. Optimization goal could be minimizing energy or maintaining the battery life or things like that, and constraints are going to be all these things that I have listed. So I notice I'm at like 5:45 right now, so I'm not going to start on those strategies and pick it up on Wednesday. But essentially, this is what you have to do in any system. And I must emphasize that again, the concepts that I'm presenting, you really can scale them to different parts of the computing system and indeed to other classes of systems beyond computers. So let's reconnect on Wednesday.